record. All right, perfect. So when we talk about limits, all right, what is a limit? A limit is just the value your function approaches as it gets close to some x. Okay, that's all a limit is. Right? We want to be able to get as close to that limit as we want by getting as close to that x as we want. And finding a limit should be exceptionally easy a lot of the time. If you just take a limit, and if I say what's the limit as x approaches 3 of x squared plus 9 over x minus 5, what should you be doing? In fact, what should you do with every limit immediately?
Substitute the
plug
3
in.
Yeah, just plug that 3 in, right? So 3 squared is 9 plus 9 is 18 over 3 minus 5 is negative 2. Your limit is negative 9. Right? If this comes out to be some number, you are done, right? Negative 9 is a number, right? That's the answer. Limit's done. Plug it in first thing, 100% of the time, plug it in. All right? Everyone's good with that, I hope. Yes? Responding is good. Okay. So next thing that might happen, sometimes you might be working through your limit and you might get something like, you might not get negative 9. You might get something like 2 over 0. Right? If we get 2 over 0, then we will say that this limit does not exist. And in fact, 2 over 0, we would be able to say that if this is approaching 0 from the right-hand side, that this limit could be infinity. Or if we're approaching it from the left-hand side, it could be negative infinity. But we want to remember that anytime a limit is infinity or negative infinity, it technically doesn't exist. And so if you're sitting there doing multiple choice questions, first off, they might put the limit as infinity, or they might put the limit doesn't exist. Okay? But if they put both of those things, then you can be guaranteed that neither of those is the answer choice, because a limit that is infinite is the same as a limit that doesn't exist. So you can just pick one of the other options and know that it's not either of those if both of those appear. If you get something like 0 over 2, please don't think that that's something weird. That's just 0, right? That's just 0. Yeah. Everybody good with the basic idea of limits when we just get a number or some number over 0?
Yep.
Wonderful. Okay. Spectacular. What if we end up with something like 1 over something that's infinite or a very, very, very large number? Right? This thing is going towards infinity in the denominator, or any constant over infinity. What does that become?
0.
0.
It becomes 0. Okay, everybody good with that? So if those pop up with your limits, that's what you should do. Now, the problem starts when we end up with an indeterminate form. And there are really 2 main indeterminate forms that we are worried about for this class, 0 over 0 and infinity over infinity. Every once in a while, this one pops up. 0 times infinity. 0 times infinity can always be rewritten into one of these 2 forms of 0 over 0 or infinity over infinity. If you end up with one of these limits, 0 over 0 or infinity over infinity, you have a bunch of different options about how to solve it. Usually the easiest way, and I will recommend that usually you use this, is L'Hopital's rule, right? Which of course we know that in order to use L'Hopital's rule, we have to know how to take derivatives, right? So if the limit is 0 over 0 or infinity over infinity, then you just take the derivative of the top and you take the derivative of the bottom. And that's your new function that you're looking for the limit of, and you just evaluate it. And you do not take the derivative of the function as a whole. So if I have something like the limit as x approaches 3 of x squared minus 9 over x minus 3, we'll note that if we plug in 3, this is 0 over 0. We just use L'Hopital's rule, and on the test, in the free response, you will write out that you are using L'Hopital's rule. You won't abbreviate it LH, you will write it all the way out. L'Hopital's rule, using L'Hopital's rule, this limit becomes the limit as x approaches 3 of the derivative of x squared minus 9 over the derivative of x minus 3. You reevaluate and you get 6. Everybody good with that?
Yep.
Wonderful. Okay. You can reapply L'Hopital's rule as many times as you need to reapply L'Hopital's rule. So if I took the derivative of this and it came out to be 0 over 0 or infinity over infinity again, I can apply it again, take a second derivative of the top and a second derivative of the bottom. And hopefully it's not 0 over 0 or infinity over infinity. You can keep doing it until you get to something that is not 0 over 0 or infinity over infinity. Please do not try to use L'Hopital's rule for anything other than these two forms, right? Only for these two forms. If you try to use L'Hopital's rule for just any regular old limit that's not 0 over 0 or infinity over infinity, you will get the wrong answer. It has to be indeterminate. Okay? What's something else we could have done to solve this one if we needed to?
Factoring.
Sure.
Yeah, we could have factored it, right? We could have factored x plus 3x minus 3 over x minus 3, canceled the x minus 3s. I think L'Hopital's rule is quicker and easier, but that's just up to you. If you want to do the factoring way, you can. We have some other things that we can do. One of them is multiplying by the conjugate, right? We're not going to do one like that because if you multiply by the conjugate, that's a lot of algebra, and the steps for L'Hopital's rule will be easier than these steps for multiplying by the conjugate. So there's really no reason for you need to multiply by the conjugate on the AP test to solve a limit. Everybody good there?
Yes.
Okay. Now the question then becomes, how might I get infinity over infinity? Well, there's a couple different ways to get infinity over infinity. Something like the limit as x approaches infinity of, let's say, e to the x over x to the third power. All right, so if we look at this, this is infinity over infinity. True? Everyone agree with that? Both of those are going towards infinity?
Yes. So
we'd write out using L'Hopital's rule, this would become the limit as x approaches infinity of e to the x over 3x squared. And we find that that is still infinity over infinity, right? So we could do it again using L'Hopital's rule a second time, and we'd say this is now the limit as x approaches infinity of e to the x over 6x, which is still infinity over infinity. And we could, if we wanted to, write out L'Hopital's rule again and get e to the x over 6, and we would find now this is infinity over 6. And infinity divided by 6 is still just infinity. So you could say this limit doesn't exist, or you could say that this limit is infinite. But you don't really need to write all that out. And oftentimes they will put limits just like these ones in the multiple choice. And so you can do L'Hopital's rule a bunch of times to see what you get, or you can just know the order in which functions increase and which functions increase more rapidly than other functions. So for example, we know that e to the x increases more quickly than x cubed. So over time, the numerator is going to get larger more quickly than the denominator. If the numerator gets larger more quickly than the denominator, we're going towards infinity. If the denominator gets larger more quickly, then it should be going towards
Zero.
Zero. Exactly. Perfect. Everybody feel okay about that?
Yes.
Great. Everyone's good? No questions? Okay. Exponential functions will grow most quickly. Okay. Depending on the base, the higher the base, the more quickly it grows. So 2 to the x will grow more slowly than e to the x because e is more than 2. E is between 2 and 3. So 3 to the x grows more quickly than e to the x. 10 to the x grows more quickly than 3 to the x. Next one down the line after exponential growth that still goes towards infinity should be any sort of polynomial growth, right? Like x cubed or x to the 700th minus x to the 500th plus x to the 384th. That will grow less quickly than exponential over time, but more quickly than the basic of our polynomial functions, a linear function, right? A linear function like 6x will still go towards infinity, but it grows less quickly than any other polynomial function. Next, slowest is root functions, okay? Square root, cube root, fourth root, seventh root, etc. The larger the root, the slower it grows. So like the 10th root of something will grow less quickly than the square root of something. And then lastly, over time is logarithmic functions. A logarithmic function will increase the least rapidly of anything that's going towards infinity. Does that make sense to everybody? So if you know this order, you should be able to solve these pretty easily. these often show up. A lot of times these show up where they'll give you like 3 different limits like this, like e to the x over x cubed, x to the 100th over the square root of, 17x squared, and, things like that. And they'll say, which of these limits go towards infinity, or which of these limits equals 0? And so if you know the order, it's easy for you to just, quickly go through and say, all right, this one's 0 because the top goes to infinity less quickly than the denominator. This one's also 0 because of that. This one's infinity. And so you can pick the 2 that go to 0. Does that make sense, everyone? Conceptually, like what I'm saying there?
Yeah.
Perfect. Okay, let's see here. So another way that we might end up with something that's infinity over infinity, and they will, occasionally once every couple of years, they put these on. And since there was no multiple choice last year, it's hard for me to make a judgment about it. But suppose we were going towards pi over 2 from the left, and we had the function secant x over, I don't know, about 2 plus tangent x. And we note that as we plug in pi over 2 to secant, because that's 1 over cosine. What's the cosine of pi over 2? Cosine of pi over 2 is 0, right? So this is 1 over going towards 0. So 1 divided by a very small number becomes a very, very large number, right? So this becomes infinity. And the same thing with this. This becomes 2 plus the sine of pi over 2, which is 1 over also 0, right? Cosine of pi over 2 is still going towards 0. So this becomes infinity over infinity. Everybody good with that?
Yes.
Okay, so what we would do is we'd write out that we're using L'Hopital's rule. And we take the derivative of secant to get secant x tangent x, and we take the derivative of 2 to get 0, and the derivative of tangent to get secant squared x. And we'd simplify. So we'd simplify this down to the limit as x approaches pi over 2 from the left of tangent x over secant x. And what we note is that this is still infinity over infinity, right? Because the tangent's still giving me infinity and the secant's still giving me infinity. And if we tried to use L'Hopital's rule again, we'd end up with secant squared over secant tangent. And that'd just be secant over tangent, which would be infinity over infinity. And if I tried to do it again, I'd get infinity over infinity again and again and again. I just flip back and forth between tangent over secant and secant over tangent. So what we need to do is we need to rewrite these in terms of sine and cosine. And this is something that pops up fairly often. So we'll have sine x over cosine x over 1 over cosine x. And we can then cancel out the cosine x's, and we just get the limit as x approaches pi over 2 from the left of sine x. And what's the limit as x approaches pi over 2 of sine x? That's just the sine of pi over 2. You just plug it in, gives you 1. Does that make sense to everybody? So that's a common problem that you might see in the multiple choice, something like that. Somebody asked about, wouldn't 1 over 0 be undefined? Yeah, 1 over 0 is undefined, but remember that this is not 1 over 0. This is 1 over approaching 0 from the left-hand side, right? 1 over approaching 0 is 1 over a very, very small number, and 1 divided by a very, very small number becomes a very, very large number. That's why we get infinity there. Does that make sense? Perfect. Okay. All right. So there are our 0 over 0 and infinity over infinity. Now, we didn't really talk about this one, 0 times infinity. So 0 times infinity, they like to put this type of problem, something similar to this, on the test. Right? X sine 1 over x. Or they might have it written as, sometimes they'll write it like this, which is not 0 times infinity. They'll write sine 1 over x over 1 over x, which is 0 over 0. So if you see this, right, one of those two forms, you need to recognize that that's indeterminate, because as x goes towards infinity, this is infinity times the sine of 1 over infinity, and that's the sine of 0. So that's 0 times infinity. And so what we need to do is rewrite it in that form that I just had, that I said sometimes they'll put it like that on the review test, sine of 1 over x over 1 over x. And then, because this is now 0 over 0, we can use L'Hopital's rule and and just take the derivative of the top and the derivative of the bottom, you get the limit as x approaches infinity of the cosine of 1 over x times negative 1 over x squared. That's the derivative of 1 over x, and then over negative 1 over x squared. And those negative 1 over x squared will just cancel, and you're just left with cosine of 1 over x, which when we plug in infinity is cosine of 0, which is 1. That's one option for doing that one. Another good option for doing this problem is at this point right here, we could let u equal 1 over x. We let u equal 1 over x. As x approaches infinity, u begins to approach 0. And so this limit turns into the limit as u approaches 0 of the sine of u over u. And that's a limit that is a known limit that we should have memorized. We know that that one's just 1. Even though it's 0 over 0, we've proven a couple different ways that that's 1. One way we could do it is just take the derivative of the top and the derivative of the bottom and get cosine u over 1. But this is one of the limits that you should just know. Everybody good with that?
Yes.
Any questions so far? My wife has a question. Is it about math? Okay. She's just trolling me during my review session here. That's fine. Okay, so the limits that you need to know, we have the one that we just did, right? The limit as x approaches 0 of sine x over x. That one's equal to 1. You should also know, and these are on that sheet that I sent out to you all, that the limit as x approaches 0 of x over sine x is also 1. That the limit as x approaches 0 of tangent x over x is also 1. And that the limit as x approaches 0 of x over tangent x is also 1. And we should also know that the limit as x approaches 0 of 1 minus cosine x over x is 0. And the limit as x approaches 0 of cosine x minus 1 over x is also 0. These ones pop up fairly often on the AP test. They're all good ones to just sort of have memorized. They're all indeterminate, so they can all be done using L'Hopital's rule, but to just know them will make your life a lot easier. So that's close to all there is about like algebraically evaluating limits. There's one more type of problem that I want to talk about, which is something like the limit as x approaches 0 of sine cubed of 5x over 2x cubed. And so if we look at this one, we would note that if we plug in 0, we end up getting 0 over 0. And so our first instinct here might be to try to use L'Hopital's rule. And I'm going to tell you that that is a bad choice. First of all, sine cubed 5x is, I mean, it's a little unpleasant to take the derivative of. It's the chain rule within the chain rule, right? It becomes 3 sine squared 5x times cosine 5x times 5, which is a little unpleasant, over 6x squared. Well, what happens when you plug 0 into that? You end up with 0 over 0 again. So you'd have to apply L'Hopital's rule again. Now you've got something that's the chain rule within the chain rule, but also with the product rule, which is going to make life even more complicated. And I promise you, when you take the derivative of that, you're going to still end up with 0 over 0, because you're going to get a 12x down here. And then you're going to have to do it one more time to get something over 12 that's no longer going to be 0 over 0. And you don't want to go through all of that mess. That's going to be way more work than you want to do. And that's going to take you, 10 minutes to do on a multiple choice problem that you could get done in about 1 minute. So we want to remember how to pull out the constants and use some of the rules for limits. So this 2 can be pulled out as a 1/2. And we get the limit as x approaches 0 of sine 5x over x all cubed. And so now we've written this in a form that's very close to sine of x over x, or sine of u over u. All we'd have to do is throw in a 5 down here and a 5 up here to cancel those out. And then we can pull this 5 out. And when we pull it out, it's a 5 cubed. So we'll end up with 5 cubed over 2 times the limit as x approaches 0 of sine 5x over 5x cubed. And this limit, as long as the argument of the sign and the thing in the denominator are exactly the same and we're approaching 0 here, then this will still come out to be 1. So this ends up being 125 over 2 times 1 cubed, or just 125 over 2. And that will be much, much quicker and easier than trying to take all those derivatives using L'Hopital's rule. And I would say once every 2 to 3 years, they got one similar to that in the multiple choice. So that's a good little trick to have up your sleeve. Any questions on that one? Or anything we've done so far?
So you can just take out the cubed and put it outside of the limit?
That's correct, yes. The limit of a function cubed is the same as the limit of that function all cubed. That is correct. That's one of our rules for limits.
Cool.
Yep. All right. I believe when we talk, well, let's not say that we're done with algebraically evaluating limits. Let's talk about this. We have something like the limit as x approaches infinity of x squared plus 5x minus 1 over 3x squared plus 7x minus 4. There are a couple of ways to do this limit. The most difficult way is you can divide everything by x squared and divide by the highest power. That's going to eventually get a bunch of terms that cancel out to 0, and you're going to get an answer of 1/3. We're not going to do that. The next thing that you can do is you can say, all right, this is infinity over infinity, so I'm going to use L'Hopital's rule and get 2x plus 5 over 6x plus 7. And you will write the limit in front of it, and you will write using L'Hopital's rule, and you'll see that it's infinity over infinity. And then you'll do the same thing again to get 2 over 6 and get your answer of 1/3. Right? And that's fine. But if this is in the multiple choice, you can recognize that talking about a limit as x approaches infinity is talking about a horizontal asymptote to the right. And you want to be able to know the rules for horizontal asymptotes of rational functions, right? This is just a rational function. So if the degree of the numerator and the degree of the denominator are the same, just divide the leading coefficients. If the degree of the numerator is more than the degree of the denominator, then you know that this thing will eventually be going towards infinity, and there is no horizontal asymptote. And if the degree of the numerator is less than the degree of the denominator, remember this is only for rational functions, this will go towards 0. So the limit as x approaches infinity of this first one is 1/3. Second one would be infinity, or it doesn't exist. The third one would be 0. And if you are asked to prove horizontal asymptotes, you need to somehow prove the limits, and then you need to show to the right and to the left. So you'd have to do it for negative infinity as well. Everybody good with that?
Yes.
And we'll want to note that for a rational function, a polynomial over a polynomial, the horizontal asymptote to the right and the horizontal asymptote to the left will be the same, always, for a rational function. I'm not sure what your question is, Karina. Only for x to infinity? You mean like, yeah, only if you're evaluating a limit as x approaches infinity or negative infinity can you do this. If I say what's the limit as x approaches 2, you just plug in 2 and get some number. Is that what you mean? Yeah, okay, cool. Now, sometimes they will be unkind to you and they will ask you either this question, which isn't so bad. Pretend that you can read that and it says infinity. This question, or, man, that's just awful. Let's try this again. Or they will ask you about this limit, or something similar to one of these. Now, this one on the top is easy, right? Square root of x squared plus 1. Well, really, that as we go towards infinity, the plus 1 is insignificant, and the square root of x squared, because the number I'm plugging in is positive, just comes out to be x. This is effectively x over 2x, which is just a half. But over here with this one, we have to remember that the square root of x squared equals x only if x is greater than or equal to 0. the square root of x squared is the opposite of x if x is less than 0. And since the limit that we're looking at here is approaching negative infinity, our x values are negative. And so this is the case we're talking about. So as that plus 1 becomes insignificant, just like the minus 1 does, we simplify this down then to, instead of the square root of x squared, we simplify it to negative x over 2x. Then the x's cancel, and you end up with negative 1/2. So it's pretty common for them to put one like this in the multiple choice. It's usually one of the most commonly missed problems in the multiple choice. So don't let that fool you, right? This is not a rational function. The limit to the right and the left are not the same. Of different horizontal asymptotes in different directions. Everybody good there?
Mr. Bachelor?
Yes.
Why do you have to take the square root first when you're doing the square root of x squared?
What do you mean, why do you have to take the square root first?
Because that's what would make it negative x, right? Because if you had negative infinity squared, wouldn't that just be infinity and then the square root of that?
Yes, it is. But okay, so this is the part where it starts to confuse people. And so you're right. If I have a negative number and I plug it in there and I square it, I get a positive, then I square root it and I still get a positive, right? So what I end up with, though, is not x. I don't end up with x, right? Because what did I plug in for x? I plugged in a negative number, but I got out a positive, didn't I?
Yeah.
So I didn't really get out x. I got out the opposite of x, right? Because x was a negative number when I plugged it in. So my final result is actually the opposite of x, which is a positive number. Does that make sense?
Yeah, so if the number that you plug in is negative, then your answer has to be negative.
That is, well, you're talking the final answer?
Just for that situation of where it's square root of x squared.
Correct. You need to get a negative x out of that. If the x value that you're plugging in is a negative number, you need to get a negative x. That's correct. The final answer doesn't have to be negative, because if I threw a negative 2x minus 1 down there, then my final answer is actually positive. But
yeah. Okay, thank you.
Yep, no problem. All right, any other questions on that? Because this one's kind of the sticking point. People don't like this problem. People always miss that problem when I put it on the test every year, and then on the AP test, they miss it also. So, any questions or issues there? Everybody good? All right. So that is about it for basic limits algebraically. I think that is it for limits algebraically. What we then need to talk about is what happens when we look at a graph, because oftentimes they will give you a graph and they will say, well, find the limits based on this graph of whatever things whatever things they might ask you about. So let's sketch a simple little graph here. Let's say it looks like this. Yeah, let's put a point right there. Let's call this 1. Let's call this 2. We'll call this 1. Call that negative 1. We'll call that negative 2. Sound good to everybody?
Yep.
Cool. All right. So I might ask you, what's the limit as x approaches negative 2 from the right of our function f of x? What should the answer be?
0.
Should be 0, because as I approach negative 2 from the right, it's 0. What if I asked you, what about the limit as x approaches negative 2 from the left of f of x?
Also 0?
Is there anything to the left here of negative 2?
No, so you could say it doesn't exist?
Correct. There is no function to the left of negative 2. That limit does not exist. Okay? Which tells us that the limit as x approaches negative 2 of f of x, the two-sided limit, also does not exist. Because the rule for two-sided limits is that in order for a two-sided limit to exist, the left and the right limits have to be equal. They both have to exist and they both have to be the same. So in this case, one of them was 0, the other didn't exist, so our two-sided limit couldn't exist. What if we talk about the limit as x approaches negative 1 from the left? What should that be?
0.
0. What if we approach -1 from the right?
Also 0.
Also 0. Therefore, we are guaranteed that the limit as x approaches -1 is 0, no matter what. Even if I put in some point up here that's at -1, the limit is still 0 because the limit from the left and the limit from the right are both 0. This extra point doesn't do anything for us. Good?
Yep.
All right, and what about the limit as x approaches 1 from the left? That should be
2.
2.
And our limit as x approaches 1 from the right ought to be
0.
0, and therefore the limit as x approaches 1 of our function does not exist, even though the two limits both exist. The two-sided limit doesn't exist because the one-sided limits are not equal to each other. Good?
Good.
Yes.
Wonderful. All right. The last thing that we will talk about with limits is, I think it should be the last thing. I think we've talked about everything else. Yep. Is the limit definition of the derivative. Right, the limit definition of the derivative is something that pops up in the multiple choice fairly often. Remember that the limit as h approaches 0 of f of x plus h minus f of x all over h is one form of the limit definition of the derivative. The other form is the limit as x approaches a of f of x minus f of a all over x minus a. So you might see a multiple choice question where they are utilizing these. And before I get into what the questions might look like, remember that this piece here, this thing is called the difference quotient. So if they do say something like, oh, the limit is, what's the limit as h approaches 0 of the difference quotient of some function, you know that that just means the derivative of that function. So oftentimes they may put something in like, what's the limit as h approaches 0 of, let's say, the sine of pi over 3 plus h minus the square root of 3 over 2 all over h. And you'll look at that and say, that limit looks atrocious and awful and I don't want to deal with it, is probably what you'll say, right? That sound about right? Maybe. Okay. Yep. But what you'll note is that, first of all, what's the first thing you should do is you should just plug in 0, right? Sine of pi over 3 is root 3 over 2, minus root 3 over 2 is 0 over 0. So it's indeterminate. So the first thing that you could do is you could say, all right, I just need to take the derivative of the top, and I need to take the derivative of the bottom. Right? So you could do that and get the limit as h approaches 0 of the cosine of pi over 3 plus h minus 0 over 1. And we'd note that that should just be the cosine of pi over 3, which is a half. We might also note, though, that this is in the form of the limit definition of the derivative. This is the function is sine. So we've got sine of pi over 3, that's my x value, plus h, minus sine of pi over 3, which is root 3 over 2, all over h. So we could recognize that this is just the derivative of sine x at pi over 3. And the derivative of sine x is cosine x. And so that'd be the cosine of pi over 3, which is a half. So either way you do it is fine. But I won't guarantee that you'll see one of these in the multiple choice, but they show up most years. So you might not have one this year, but usually there is one. Good with that?
Yes.
All right. Oh, a couple other things I want to talk about before we really move full bore into derivatives. One is the extreme value theorem. And every once in a while, I'll throw in a multiple choice or something in the free response that involves this. The extreme value theorem says that if f is continuous on the closed interval a to b, f has an absolute max and an absolute min on that interval. Okay. So a couple of important things to note about this is that that means that if you are ever asked to find an absolute max or a min, and you are given a closed interval, you want to remember to check the endpoints because the endpoints could be the absolute max or min. You'll also have to check the critical values, which we'll talk about finding in a bit. Okay. But sometimes they will put a question in the multiple choice that says something like, f is defined, and they'll say something like, f is defined on A to B, but has no max or has no min. What must be true? Well, f is defined on A to B, but has no max, does not mean that f is continuous. So we would have to say that f is not continuous. And it's easy enough to draw an example of this. I mean, here's, you know, here's A, here's B. This is defined from A to B, every value, right? Defined at A, defined at B, defined at everything between A and B, but has no absolute max or no absolute min. I get very, very close to whatever this y value is up here, but I never get to it, so there's no absolute max. And I get very, very close to 0 down here, but I never get to it because there's no min down there. And these points are clearly not absolute maxes or min because there's plenty of points below and above them. Make sense?
I'm sorry, this is probably a really ridiculous example to bring up, but how would this work for something like a horizontal line?
For something like a horizontal line, yeah, so that's fine. That's a good question. A horizontal line, so here is A to B, we'll say it's continuous on this interval from A to B, and that's fine. Let's say this value is 2, okay? 2 is the absolute max. 2 is also the absolute min. And the absolute max and the absolute min both occur an infinite number of times between A and B at every single x value between A and B. So the definition of an absolute max or an absolute min is that it is greater than or equal to, or it is less than or equal to all other y values on the interval.
Got it, thank you.
So both of those are satisfied. 2 is both greater than or equal to 2 for this entire interval, and it is also less than or equal to 2 on that entire interval. Does that make sense?
Yeah, thank you.
What if it was open circles at an A and B?
If it was open circles at A and B, this one would still have an absolute max of 2 at everything between A and B, just not at A and B, and also an absolute min if it was open circles there. That'd be fine. Just because a function is not continuous on the full interval from A to B does not mean that it doesn't have an absolute max. This is a one-way street here. This is if the function is continuous, it has an absolute max and min. But you can't say that the converse of that is true, that if it has an absolute max and min, it must be continuous, right? So it's not, like I said, it's not a two-way street, it's a one-way street. Like I could draw something like this, that is, sorry, that is, I don't want it to be continuous, sorry. That is not continuous from A to B, but it does have an absolute max and it does have an absolute min. So that's fine. Does that make sense?
Yeah.
Cool. Any other questions on the extreme value theorem there? All right, the next one is the intermediate value theorem. I'll talk briefly about this. The intermediate value theorem just says that if f is continuous on A to B, then any f of C on the interval from f of A to f of B can be obtained through some C, that's supposed to be a C, some C on the interval from A to B. So effectively it says, if I start here and I end here and my function is continuous, doesn't matter how I get there, every single value between f of B and f of A, so all the y values between f of A and f of B, can be found by picking some value of C between A and B. I pick this one, let's say. I can find that right here. That's between A and B. I can also find it right here. That's between A and B. And it doesn't mean that every value that's between here must be between A and B. I might have my function continuing like this, and I have a value between f of A and f of B that is not between A and B, but it's possible to find this value between A and B. And it also doesn't mean that there might be values that extend out of it, out of f of A to f of B. That's okay. It just means that if I pick something between f of A and f of B, I can get that from something between A and B. And this is often used to show that there's a x-intercept or a root or a zero of a function, because if I start here at A and I finish here at B, I'm going to see that there was a sign change. And according to the intermediate value theorem, if the function is continuous on A to B and f of A and f of B have different signs, I must have crossed through the x-axis, and I must have got a root or a zero or an x-intercept or whatever you want to call it. Does that make sense to everybody?
Yes.
Cool. And this will, they sometimes will throw this into like, into a multiple choice question that just looks kind of annoying. Like it's a whole bunch of, a whole bunch of reading that you'll have to do. And then it'll be like, f is continuous, and it'll say like f of A equals 7, and f of B is equal to, in fact, this is something like they usually use numbers instead of f of A. So like f of 1 is equal to 1, and f of 4 is equal to 16. And then they'll give you a bunch of like ridiculous answer choices like, oh, f of 2 must be 4, f of 3 must be 9, f must always be increasing. Or it might say like something, and then they'll have one that's like f of 15 has a solution on A to B, or on 1 to 4. And so f of 2 doesn't, it sure looks like 1 squared is 1 and 4 squared is 16. So 2 squared should be 4 and 3 squared should be 9. But nothing in there said that this was the function x squared. So these aren't guaranteed to be true. And f looks like it's increasing, goes from 1 to 16. I would say f is increasing on 1 to 4. Well, that's not necessarily true. I could have had f of 1 is 1, and f of 2, could be negative 1,000. I was definitely decreasing, and then I made it back to 16 for f of 4. But f of 15, sorry, not f of 15, but f of, I shouldn't have written f of 15. I wrote that poorly. That's not what I meant to write. Something like f of x equals 15 has a solution on 1 to 4 means that I can find an x value between 1 and 4 that gives me a function value of 15, because f is continuous and it went from 1 to 16, 15 included on that. So somewhere between 1 and 4, I must have hit that value of 15, at least once. Does that make sense to everyone?
Yeah.
Okay, that's the intermediate value theorem. And that's kind of the way that they might throw that into the multiple choice. Sometimes they might give you a chart of values, and you got to look at the chart of values and see, that if I went from 1 to 16 on the chart, that I must have hit 15 somewhere in there, even though 15 didn't show up in the chart. And when you read the words in front of charts and functions that they give you, they will often put things in there like, it'll say that the function is continuous and differentiable, or it'll say it's continuous and differentiable and increasing on the full interval. So just make sure you note those things, because usually when they tell you that, there's a reason they're telling you that. There's something important about that that's you're going to need in the problem that they're giving. Does that make sense to everyone? Everybody doing
Makes
okay?
sense. Yeah, it makes sense.
I have a question. So
Yeah.
when you're on the first response and you use IVT, would you put the interval in closed or open brackets?
It should normally be in closed brackets. I think some textbooks put it in open brackets, but closed brackets is really the better way to do it. So, you can, okay, so it depends. If you want to just say, you can do it with open brackets. Closed brackets is fine. You can also do it with open brackets. It just means then that you're not guaranteed a value of 1 or 16 on the open interval between 1 and 4. You're guaranteed all the values between 1 and 16. So either way you want to do it, they'll be fine with. I've seen, in fact, and I've seen them write it. I've seen kids like answers, because they send me answer choice or answers that kids have written out for things. And I've seen them accept both brackets and parentheses with IVT. So you're good either way.
Okay, thanks.
Uh-huh. All right, last thing before we go into derivatives, because this popped into my head here a second ago, is continuity also. So we talk about continuity at a point, and this is something that they really do like to talk about and ask you a question on. There are 3 criteria to prove that something is continuous at a point. So if we want continuity at a point C, we would say that f of C has to exist. We would have to say that the limit as x approaches C of f of x has to exist. And we would say that the limit as x approaches C of f of x has to equal f of C. So it has to meet all 3 of the all 3 of these criteria for a function to be continuous at a point C. Yeah, so Patrick, I see your message. I will get to this parenthesis bracket question that you're asking about in about 10 or 15 minutes once I get to some of the stuff we're talking about with derivatives. So I will definitely talk about that in a minute, okay? Cool. All right, so this idea of continuity at a point usually comes up in something like, they'll give you a piecewise defined function. They'll say the limit, or no, they won't say the limit. They'll say, you know, f of x is equal to x squared minus 1 if x is less than 2, and they'll be like, f of x is equal to, I don't know, x plus 2 if x is greater than or equal to 2, something like that. And you would then need to see if all 3 of these criteria are true to see if this function is continuous at 2. So really you're just seeing, does the value at 2 in this match up with the value in 2 at this? If it's in the multiple choice, just plug 2 into this and 2 into this and see if they're the same. If they are, it's continuous at that point. If they're not, then it's not. But if you're doing it on a free response question, and occasionally they will say, you know, explain why this is continuous, you need to write it out in the limit notation. You say the limit as x approaches 2 from the left of f of x is 2 squared minus 1, or 3. And the limit as x approaches 2 from the right of f of x is just 2 plus 2, so it's 4. And since those are not equal to each other, that does not meet criteria number 2. The limit does not exist because the left and the right hand are not the same. Does that make sense to everybody there?
Yep.
Cool. Now, they also will sometimes ask about if something is differentiable for all real numbers or differentiable at a specific point, given a similar setup. So they might say f of x is x squared plus 1 if x is less than or equal to 2, and it's x plus 3 if x is greater than 2. And so for a function to be differentiable, or for a function to have a derivative at a point, the function number 1 has to be continuous at that point. So we have to check the continuity just like we did a second ago. So we do, and we write it out the limits. 2 squared plus 1 would be 5, and 2 plus 3 would be 5. So we see that it's continuous there. And since it's continuous there, we then go in and we take the derivative, right? Our derivative would be 2x if x is less than or equal to 2, and it would be 1 if x is greater than 2, and we would see that, well, this is 4 and this is 1, and since the derivatives aren't the same from the left and the right, it's not differentiable, but it is continuous at that point. Does that make sense to everybody? And so sometimes they'll ask that in the multiple choice.
Okay, so derivatives work kind of the same way as limits in terms of figuring out like if a derivative exists at a point?
That is correct. Yep, because remember that a derivative is just a limit, right? So the derivative from the left and the derivative from the right are just the limit as h approaches 0 from the left of fx plus h minus f of x over h, and the limit as h approaches 0 from the right of that.
Cool, thank you.
And so sometimes they will try to trick you into something like this. They'll say f of x equals, and they'll put in like x squared plus 1 if x is less than or equal to 2. And they'll say, now let's use it. Let's say x is less than or equal to 1. And then they'll say something like it's equal to 2x. No, that's not what I want. Let's go x squared plus 4. And then 2x if x is greater than 1. And so a lot of people will skip checking for continuity, and they will go straight to checking the differentiability based on the derivative. So you get 2x if x is less than or equal to 1, which would give you 2. And you'd get f prime is 2 if x is greater than 1, which would give you 2. And you'd say, oh, cool, it's differentiable. Well, no, it's not differentiable because you didn't go and check the continuity. 1 squared plus 4 is 5. And 2 times 1 is 2. So the function is not continuous. It's got a hole at the point where x equals 1. And a hole means that it can't be differentiable. Now the slopes from the left side and the slopes from the right side are the same, but a derivative can't exist at a discontinuity. So be extra careful to make sure you check for the continuity if they give you a piecewise function and ask if it's differentiable. Everybody good with that?
Yep.
All right. Now, go ahead.
So something can't be differentiable and not continuous.
All I heard was something can be not differentiable, but then I couldn't hear the end.
So something can't be differentiable but not continuous.
Something cannot be differentiable and discontinuous at the same point.
Okay.
Yes. And somebody was just asking, what does not differentiable mean? Not differentiable at a point means that the derivative at that point doesn't exist. And so I was just about to say, there are 4 reasons why a derivative might not exist at a point. And you want to know why or what those things are. F prime does not exist, 1, at a discontinuity, which is what we were just talking about. 2, at a corner, so like an absolute value function or something like that. 3, at a cusp where you're coming in like this. And 4, at a vertical tangent line. So something like that, where the tangent line is vertical. The slope of the function there is undefined because the slope of a vertical line is undefined. And so if the slope of the tangent line is undefined, that means that the derivative is undefined. So these are the 4 things that make a derivative not exist at a specific point. If one of those things happens, if you have a discontinuity, corner, cusp, or vertical tangent. Does that make sense to everybody?
Yep.
Excellent. Any questions so far before we get into taking our derivatives and what derivatives and second derivatives and all that fun junk means? All right, before we do that, because I just happened to think of one other thing, the squeeze theorem, right? Squeeze or sandwich theorem doesn't pop up very often, but it might. Just remember, and it usually won't be in the context of something super difficult. They will just give you some information like that f of x is less than or equal to g of x is less than or equal to h of x on some interval. And they will say that the limit as x approaches, I don't know, we'll say 1 of f of x equals 5. And the limit as x approaches 1 of h of x is 5. Therefore, by the sandwich theorem or the squeeze theorem, the limit as x approaches 1 of g of x is 5. And so they might, they might give you 2 functions that are always less than or equal to some other function or greater than or equal to some other function. And then they might have you, find the limits of those at some certain point to indicate if they're the same, that the limit of the other one is also the same. If they're not the same, then it tells you nothing about the limit of the one that is squeezed between the 2. So that's just real quick. Just keep the sandwich theorem in mind. Chances of you having to use it are not real likely, but at least need to mention it and say what it is again. Right? If this is true, then the limit at any value here that is equal to the limit of h, so the limit of f and the limit of h are the same, then the limit of g must be also. All right, taking derivatives. Now, I'm not going to take a bunch of derivatives. I'm not just going to like write down a bunch of simple functions and take derivatives. We should know how to take most of our derivatives, right? The derivative of a constant is always 0. The derivative of any polynomial function, we will just use the power rule. If you've made it this far and can't do the power rule, you're in a lot of trouble on the test. So hopefully you can do the power rule. We will talk quickly about the product and the quotient rule, just because I want to reiterate that anytime you have a product of two functions or a quotient of two functions, you must use the product rule. All right, so if we're looking at u times v, it should be u prime v plus v prime u. And if we're looking at u over v, you need to do v u prime minus u v prime over v squared. Don't forget that. This also applies when you're going into doing implicit differentiation. If you see something like xy that you need to differentiate, you need to do x times the derivative of y plus y times the derivative of x. A lot of people just go in and try to like call this, 1 times dy dx if we're differentiating with respect to x, but that's not the case. It needs to be x times the derivative of y plus y times the derivative of x, right? We'll talk more about implicit differentiation in a bit, but just don't forget that it applies, the product and quotient rules apply in there also. Good or no? Okay, next thing is the chain rule. The majority of the derivatives that you will need to take on the AP test will use the chain rule. The chain rule is for finding the derivative of a composition of two functions, f of g of x. It is helpful to know two different things. One, that the derivative of this is f prime of g of x times g prime of x. So if you see what's the derivative of f of g, know that it's f prime of g times g prime. And they love to put these into little charts where they'll give you x and they'll give you f and they'll give you f prime, they'll give you g, they'll give you g prime, and they'll give you values of like 0, 1, 2, 3, etc. And then they'll put in things like, I don't know, they'll just put in some values here like 2 and 4 and 6 and 3 and let's see here. Let's see, we'll put a 3 in there and we'll put in a 2 and a 5 and a 1 and a 6 and a 4 and a -2 and a -1 and 5, 6, 8, 2. Some chart like that. And they might say, what is the derivative of this at x equals 1, right? So if they ask you, what's the derivative of this at x equals 1, you can just go straight to this formula. It's f prime of g of 1 times g prime of 1. So then we need to find g of 1 by going to our chart. G of 1 is 3, so this becomes f prime of 3 times g prime of 1. G prime of 1 is 1. F prime of 3 is 6. So this becomes 6 times 1, gives us 6. That make sense?
Yes.
Wonderful. They also might, and they really like to do these kinds of problems with charts on the AP test. So they might say, okay, instead, let's say m of x is f times g. What is m prime of 1? Well, m prime of 1 ought to be f prime of 1 g of 1 plus g prime of 1 f of 1. And then you'll just find all those values in your chart and you'll plug them all in. They might say that it's f divided by g, and then you'll need to use the quotient rule. So really, when they give you this chart with one of these, some function equals f times g or f over g or f of g, they're just looking to see, do you know what that rule is? Do you know the product rule? Do you know the quotient rule? Do you know the chain rule? And can you find the values from this chart and plug them into the derivative? Should be pretty easy. And if you've been doing some of the practice tests and all that, or any of the multiple choice that I've been posting for the last couple of months, you've seen these before. So Should be good there. All right. The other thing that you might think about is when we're talking about the chain rule still, that the chain rule, if you have your composition of your functions again, we will sometimes say that the derivative of our function y is equal to dy du times du dx. And so this is important because sometimes they might say, okay, given some function dy dx equals 3x and du dx equals 7. And then they'll say at x equals 4, what is dy du? But they don't actually give you any functions. So you need to recognize that this got a dy dx, that's got a du dx. They're looking for a dy du. It is set up in this formula. So dy dx, 3x, needs to equal dy du, the thing we're looking for, times du dx, which is 7, when x is 4. So 12 equals dy du times 7, or dy du is 12 over 7. Does that make sense? They really like these questions with notation in them. But it's also just important for us to be able to take derivatives using the chain rule. So like if I give you what's the derivative of sine squared x, we need to recognize that this is y equals u squared with u equal to sine x. And then we use that dy du, 2u times the derivative of u cosine x, and we end up with 2 sine x cosine x. Everybody good with that?
Yes.
That's just your basic chain rule, right? And note that 2 sine x cosine x pops up often enough, and that it is equivalent to sine 2x. And if you don't know all your double angle identities on that sheet of required trig that I put up, you need to go back and review all of those required trig things. If you haven't memorized them, you've got a week left to memorize them. Memorize them and be able to use them and rearrange with them. Very important. Okay, so next stuff with differentiation. We'll talk real quickly the reciprocal rule just because it might show up. If I have 1 over f of x and I want to find the derivative of that, or 2 over f of x or 7 over f of x or any constant over f of x, it's just negative and then the derivative of the denominator over that function squared. If this was a 2, we'd put a 2 up in the numerator. If it was 1,000 up here in the numerator, we'd put 1,000, negative 1,000 f prime of x. And this is just a special case of the quotient rule where the numerator is a constant, but it's helpful to know. Sometimes it'll save you some time. The other important rule that you need to know with derivatives is the inverse rule. And this is one that lots of people struggle with. It says that if f and g are inverses, and f contains a point A, B, that means that g contains a similar related point, BA, and that f prime of A is 1 over g prime of B. Okay. And this rule shows up, I would say, almost every single year in the multiple choice, almost every year. And they will say something like, they'll give you a problem and they'll say, okay, f and g are inverses. Great. And then they'll say, I want you to find f prime of 2. And then they'll give you a bunch of information. They'll say something like, f of 2 equals 3. They'll say g of 2 equals 4. They'll say g prime of 2 equals 7. They'll say g prime of 3 equals 6. They'll say g of 3 equals 5. They'll say something like f prime of 3 equals 4. No, I already used 4. Or 14, right? And they'll give you all of this unnecessary information when all you really need to do is figure out what the point that we're looking at is. F contains a point 2 comma something. Well, that's 2 comma 3. Because that's given to us. And then G contains a point that is 3 comma 2. And that f prime of 2 must just be 1 over g prime of 3. G prime of 3 is given to us as 6, so our answer is just 1/6. So it's easier than it looks, and they're going to give you a bunch of extra crap in there that you don't want to look at. You just gotta, you gotta sift through all the junk that they give you and find the two things that are important. One is, what point am I looking at? 2, 3 for F and 3, 2 for G, and then set up the inverse rule formula and get your answer. And all the rest of this was extraneous stuff that we didn't need to know. I guess I should have put a 2 there, not a 5, but everybody good there?
Yes.
Cool. That's the inverse rule. All right. Any questions on the rules and the basic derivatives and all that stuff before we move into implicit differentiation? All right. Implicit differentiation says we're going to get some function, or that's not a function. We're going to get some equation that looks like x squared y plus x equals y to the 4 plus 1. Right, some function, I keep saying function, some equation, some relation between x and y, where we can't just solve for y and then take the derivative very easily. So we use implicit differentiation and we take the derivative of both sides with respect to x. So first off, we'll do the right-hand side. Anytime you take the derivative of a y term with respect to x, you take the derivative of the function with respect to the variable that it is, so 4y cubed, and then you will multiply that by dy dx, because you took the derivative of something that was not x with respect to x. And then you take the derivative of the plus 1, you get 0. When we take the derivative of the x, we just get 1, because we're taking the derivative of x with respect to x. That's 1. Then we take the derivative of x squared y, and like we mentioned before, that's got to be the product rule. So it's x squared times the derivative of y, and the derivative of y is 1 dy dx. And then we add to that the derivative of x squared times just y. And since we didn't take the derivative of y for the second part of the product rule, it doesn't get a dy dx attached to it. Okay. Then you just need to gather all of the terms that have a dy dx onto one side. So we'll rewrite this as 2xy plus 1 equals 4y cubed dy dx minus x squared dy dx. And then we'll factor out the dy dx to get 2xy plus 1. And then when we take out the dy dx, we can see that the term that's left is 4y cubed minus x squared. Well, we'll divide by that 4y cubed minus x squared and get this as our final answer. Everybody good with that?
Yes.
All right. In terms of applications of implicit differentiation, this will show up fairly often. Well, it'll show up every time when there's a related rate question where you have to take the derivative of something with respect to t, right? And so just remember that, and we'll talk about it when we get to related rates in a bit, but just remember that when you're doing a related rate, it's implicit differentiation. You're taking the derivative of all those other terms with respect to t, so you get all these like dx dt or dz dt or dA dt terms in them that are the rate of change of that variable with respect to time. You also need to be able to find the second derivative implicitly. I'm not going to do it with this one because that one's kind of a mess. I'm going to give us an easier one. Let's suppose we have x squared plus y cubed equals x minus 1. If I were to differentiate this implicitly, we'd end up with 2x. Actually, let's make this, instead of making this x minus 1, let's make this y minus 1. We'd get 2x plus 3y squared dy dx equals dy dx. Everybody good with that? The basic implicit differentiation part?
Yeah.
Okay. Then we'd subtract the 3y squared dy dx over there. So we'd have dy dx minus 3y squared dy dx. We can factor out the dy dx and divide by what's left, which is a 1 minus 3y squared. So we get 2x over 1 minus 3y squared. Okay, so there's our first derivative. Well, to find the second derivative, we need to take the derivative of this with respect to x again. So in order to do that, we're going to have to use the quotient rule. So I'm going to just rewrite this. So we have 2x over 1 minus 3y squared. Is that right? Is that what I have? Yeah. Okay. So then we will do denominator, derivative of numerator, minus numerator, derivative of denominator, which is the derivative of a y term with respect to x. So it becomes negative 6y dy dx, all over 1 minus 3y squared. And this answer is not acceptable on the AP test. You have to go back in and replace that dy dx with 2x over 1 minus 3y squared. Okay. So you'd end up with 1 minus 3y squared times 2, and then I'll just simplify that a bit, plus 12xy times 2x over 1 minus 3y squared, all over 1 minus 3y squared. And I forgot to put that denominator squared the first time, but it should be. Yeah, that's what two of you said. Yes, that denominator should have been squared. I saw it before I even looked at what you all said. Yeah, 1 minus 3y squared, so it stays as squared. And you don't need to simplify it any further than this. Usually, they'll be asking you to like find the concavity of this implicitly defined relation. And so you'll just be evaluating these x and y values at some number. Good?
Good.
Yes.
All right, now we've gone over how to take our derivatives. Let's talk about what all of our derivatives mean. So first off, we know that the derivative is just the slope of the tangent line, right? Our derivative is the slope of the tangent line. We also just sometimes say it's the slope of the function. We will also just say that it is the instantaneous rate of change of the function. And so when we take a derivative, if we take our derivative and find f prime, and f prime happens to equal 0 or happens to be undefined at some point, this is a possible max or min. It is not guaranteed to be a max or a min. You have to make a sign chart, right? So let's say f prime of 7 equals 0. You'll put 7 on your sign chart and you'll check to the left and see, oh, it's positive, which tells us the function is increasing. And to the right is negative, which tells us it's decreasing. So we'd have a local max. So we'll note that when f prime is positive, the function increases. And when f prime is negative, the function decreases. That'll help us tell if it's a local max or min. If your chart ends up looking like this, positive and positive, there's no local max or min, right, at 7. Or if it's both decreasing, there's no local max or min. Okay. Now, who was it? Patrick, right? I think it was Patrick. A long time ago was like, I remember something about brackets and parentheses. That's right here. So they will say that if f prime is greater than 0 on an interval, f increases, right? We'll say on the interval from A to B, they say that f increases on the closed bracket A to B because they will include, and I'm going to do this right here, they'll say, we'll put brackets here, they will say greater than or equal to. And if f prime is less than or equal to 0 on A to B, then f decreases on A to B. And they indicate that with brackets, even if at that same point, like if I were to take the parabola f of x equals x squared, they would say that this is decreasing from negative infinity to 0 with a bracket, and they would say it is increasing from 0 to infinity. And so any value that you put into an increasing or decreasing interval that is not infinite, so it's not negative or positive infinity, should always be in a bracket unless that point is not defined on the function. So since f of x equals x squared is defined at 0, the brackets will go around 0 on both of them. Even though that's absurd, it's not decreasing and increasing at 0, it is doing neither at 0. That's still how they want you to indicate it. Okay. Everybody good with that?
Yes.
Okay.
Yep.
All right. Now, next thing is that if f double prime equals 0 or is undefined, actually, hold on one second. I want to go back to this slide for a second. Oh, this one. F prime is 0 or f prime is undefined, like we said, is a possible max or min. We call these values critical values. The place where the derivative is 0 or undefined is called a critical value. So if they ask you, hey, find the critical values of this function, they are asking you to figure out when the derivative is 0 or when the derivative is undefined. Okay, so just make sure you know that terminology, because sometimes they specifically use it. All right, so back to second derivatives. If f double prime is 0 or is undefined, it is a possible point of inflection, right? Remember that a point of inflection is a place where your function changes concavity. So it's possible that our function will change concavity when the second derivative is 0 or the second derivative is undefined. And so we'll have to check. When f double prime is greater than 0, the function is concave up, meaning it looks like an upward facing parabola. If f double prime is less than 0, that tells us that it is concave down and looks like a downward facing parabola. When you do intervals for concavity, you will always, 100% of the time, use parentheses. College Board gets it right on concavity, but not on increasing and decreasing. Everybody good there?
So for that, you use parentheses for everything?
No matter what. Yep.
Okay. Thank you.
And suppose we had f double prime of 3 was 0. We'd put 3 on a sign chart for a second derivative and see what happens. If it's positive here and negative here, there's a point of inflection. But if it is positive here and positive here, this is not a point of inflection. You have to look for the change in concavity. Somebody just asked about using a first derivative for the point of inflection. No, you cannot use a first derivative for a point of inflection. You must use a second derivative. The point of inflection is when the function changes concavity, which can only be indicated from a second derivative. Now, there is a way to use the second derivative to determine if something is a local max or a min. So suppose you go through and you find that f prime equals 0 at x equals, I don't know, at x equals 3, okay? Then what you can do is you can go in and look for f double prime at 3. If f double prime at 3 is greater than 0, that tells you that there is a min at x equals 3. We'll talk about why in a second. If f double prime of 3 is less than 0, that tells you that there's a max at x equals 3. And hopefully that makes sense without my explanation. But if the derivative is 0, we could have a max or a min. And the second derivative is positive, it tells us that the function is concave up at that point. So the only thing we could have at a place where we're concave up is a min. And if the function is concave down, the second derivative less than 0, the only thing we could have at that point is a maximum. That's called the second derivative test. And this is not always necessary because oftentimes you will just see it, you'll just be able to see it on a sign chart with the first derivative. But every once in a while, they will make a chart of values and ask you if there's a max or a min at some value. So they might do something like this. And I'm going to ask you 2 different questions about this. Let's say we have 1, 2, 3, 4. I guess that's good enough. And let's put in some values here. I don't know, 7, 7, 0, 0, 3, 0, 4, 6, 1, 0, 5, 0, -2. Let's say. All right, so they gave us this chart of values for f prime, and f double prime, and they would have said to us something like f is continuous and f is twice differentiable on the interval from 1 to 4. And so they might say, does f have a max or min at x equals 1? Well, you immediately go look at the first derivative. It's 0. Perfect. Must be a max or min, right? Well, but how do I determine with a sign chart on this chart? I can't. So we look at the second derivative. Second derivative is also 0. Well, that didn't follow our rule over here that if the second derivative was positive, it's a min, or the second derivative is negative, it's a max. So our answer here would be no. It does not have a max or a min at that point. But what about at x equals 2? So at x equals 2, we'd look at this and we'd say, all right, it's got a first derivative that's 0. It's got a second derivative that's positive, right? So that would tell us that this has a min. Okay. Then we might look at, what about at x equals? Well, at x equals 3. First derivative is 1? No. What about at x equals 4? First derivative is 0. Second derivative is negative. Tells us that it's a max. Everybody good with that?
Yep.
All right. Now, here's the one that they like to ask that screws people over all the time. Is it guaranteed that f has a point of inflection at x equals 3? All right, so to think about a point of inflection, we look at the second derivative. Second derivative is 0. Okay, we look for a change in concavity around that. Well, at 2, it's 4. At 4, it's -2. Sure looks like it went from concave up to concave down, doesn't it?
Yeah.
Well, I'm not sure what, oh, I don't know what that other person said. Okay, all right, it sure looks like it's changing concavity, but we are not guaranteed that between 2 and 3, it is always concave up. Suppose the value at 2.5, right? We had the 2.5 f double prime. Well, let's just try this. F double prime of 2.5 might be -100. And it might be negative all the way from 2.5 till it was 0 at 3. And then it might have stayed negative as we transitioned above 3. So even though the chart looks like it is going from concave up to concave down, we aren't guaranteed that because we don't have any information about what's going on between 2 and 3 or between 3 and 4. It could be positive all the way from 2 to 3, but then from 3 to 3.9, it could still be positive, and then it might switch to negative at 3.91 and still be negative all the way to 4. So we are not guaranteed that there is a point of inflection at x equals 3. We are guaranteed that there is a point of inflection between 2 and 4 somewhere, because it did go from concave up to concave down. It might be at 3. We can't be certain that it's at 3. Does that make sense? And they like to ask those sort of tricky questions with charts. Good or no?
Good.
Good.
Okay. Now, if they said something like f double prime is strictly decreasing from 2 to 4, well, then we'd know that it was definitely positive all the way from 2 to 3 until it hit 0, and then was definitely negative from 3 to 4. Then we could say that it did change signs at 3. And we could say there was one. Does that all make sense? That's a lot on one little chart here, but they like charts. They do like charts. All right. Okay. What else to talk about with derivatives? We've done the increasing, the decreasing, the concavity, the points of inflection. Okay, next thing we should talk about is the idea of linearization. Okay, so linearization is just a way to approximate the value of a function using its tangent line on a small interval or a small scale. Okay. And the formula for linearization is L of x is f of a plus f prime of a times x minus a, where our approximation is centered at A. So for example, if I wanted to figure out what is the square root of 17, right? The function would be f of x equals square root of x. The A value would be 16 because we know the square root of 16. And our x value would be 17. So we'd say L of 17, we'd say the square root of 17 is approximately equal to L of 17, which is f of A, so that'd be the square root of 16, plus f prime of A, well, the square root of x is 1 over 2 square root of x, so 1 over 2 root 16, times your x value minus your A value. So we'd have 4 plus, this is 1/8, or 33/8 would be a good approximation for the square root of 17 using linearization. Everybody okay with that?
Yep.
Excellent. All right. Keep in mind that we will sometimes use this in some very basic contexts, like I might say a balloon, we'll call it a spherical balloon because it'd be good to have a shape. A spherical balloon is inflated from a radius of 5 to 5.1. About how much does the volume change? And so we would use this linearization or this idea of a differential to find the approximation for how much that volume might change. We know that the volume of a sphere is 4/3 pi times the radius cubed. So we would then take the derivative, dv, and say the small change in volume is equal to, well, the derivative of 4/3 pi r cubed is 4 pi r squared dr. So it's the derivative of the volume function times the change in the radius. So our radius is 5 and our dr would be 0.1. So you get dv equals 4 pi times 25 times 0.1. So 1/10 of 100 pi, which would be, it changed by about 10 pi. That's not perfect, that's not exact, but it's pretty exact, pretty close. They like to ask those too. Good there?
Yes.
All right. Next thing that we might end up doing with derivatives is optimization problems. Surprisingly, optimization problems don't show up that often on the IDP test. There might be one of them. Usually it's one that shows up somewhere in the multiple choice. Oftentimes it involves like the Pythagorean theorem or something like that to set it up. But just remember that when you're doing optimization, all you're looking for is a max, or you're looking for a min. That's all you're doing, which means all you need to do is write a function, take its derivative, and set it equal to 0. Okay, write a function that represents that relates the variables that you're giving in the problem together in some way, a function that represents what you're trying to maximize or minimize. So if it says what's the maximum volume, write a function for volume, get it all into one variable, and then take the derivative. If it says what is the minimum surface area, write a function to represent surface area, put it in terms of one variable, and then take the derivative and set it equal to 0. Some of the common ways that you might need to get it all into one variable. So you want to keep an eye out for Pythagorean theorem. You want to keep an eye out for similar triangles. Usually the similar triangles are just angle-angle similarity. Okay? Or the relationship between volume and surface area of some geometric solid. So they'll tell you the volume needs to be this amount. You know, find the maximum surface area. So you'll write an equation for the surface area, but then you will take some information about the volume to put, let's say, R in terms of H, the radius in terms of the height, or the height in terms of the radius, or something like that. Does that make sense to everyone?
Yep.
All right. And we'll do some problems of those in the other review sessions from full AP tests. Related rates. A couple of things to remember about related rates. Number one, when you differentiate, you are differentiating implicitly. That says with respect to t, with respect to time. The same situations, these apply fairly often, the volume to surface area less often, but similar triangles, the Pythagorean theorem, show up pretty often in related rates. And you want to recognize that you can only plug in values that are not changing before taking your derivative. If you plug in values that are changing before you take the derivative, you will get the wrong answer 100% of the time. So only plug in values that are not changing before you take the derivative. Everybody good with that? So for example, if I have a situation, and this is relatively common, where we have a ladder that happens to be sliding down and the ladder is 10 feet long, right? It's okay to put that 10 because that ladder is not changing its height, right? The ladder is always 10 feet. But if I have a y and an x and I say that when x is 6, y is 8, I don't want to put 6 and 8 in here because the ladder is sliding down and y is changing, so is x. I have to leave those as x's and y's before I can go through and solve the problem. And remember that if, let's say, x is decreasing, dx dt is a negative value, right? Or if y is decreasing, dy dt is negative. If that thing is increasing, then it's a positive value. So if you forget to make your dx dt for a decreasing x negative, you will get the wrong answer. That wrong answer will probably be one of the multiple choice answers on the question. So make sure you put the negative if that value is decreasing. Everybody good with that?
Yes.
The rest of you still there and alive?
Yes.
Barely.
Hanging by a thread. We've only got 19 minutes to go according to, 18 now according to my laptop. We're not quite going to make it through everything. Maybe we will. We'll see. All right. Derivatives. Anything else with derivatives? Anybody thinking of something that I'm missing with derivatives? I can't think of anything.
Do we need to know Newton's method, or is that optional?
No. Newton's method is not required for the AP test. You will not need it. Any other questions on derivative stuff before we move into the beginnings of our integration stuff, which we will not finish, but we'll talk about at least all the approximation methods and the important stuff. Oh, we got to talk about this important thing about derivatives. Almost forgot. This is bad. All right. Wouldn't want me to forget this. Why is that line not going away? There we go. If using a tangent line to approximate the value of a function. Okay. If you are using a tangent line to approximate the value of a function, and that function is concave up, your tangent line approximation is less than the true value. If your function is concave down, your tangent line is greater than the true value. Everybody good with that? This shows up often in the free response. As you've gone through some of the differential equation ones, you've probably seen you need a second derivative to determine if it's concave up or down, and then that will tell you whether your approximation is greater than or less than the true value. Everybody good with that?
Yes.
Now, sometimes they will have you use a secant line to approximate the value of a function. Remember that a secant line is just a line that goes through 2 points of that function. It could go through more, like it could go to back down like this and go through more, but we're specifically talking about from A to B. It goes through the points A, the point at x equals A, and the point at x equals B. If your function is concave up on that interval, then your secant line approximation is less than the true value. And if it's on, did I just say less than? I just said less than. That's not right. Your secant line approximation is greater than the true value. Sorry. Right? Clearly from the picture, my secant line approximation is greater than the true value. And if my function is concave down, then my secant line approximation is less than the true value. Right? Secant line approximation less than the true value. Every once in a while, they might throw something in where they say, all right, the secant line, they'll give you the secant line and you'll approximate it using a secant line, plus they'll have you approximate it using a tangent line. And then they might ask you, which of these values is possible? And so you'd have to pick the one that's between the secant line and the tangent line's values. Right, so if I also approximated it using a tangent line right here, let's say, then the tangent line's approximation value is less than, and the secant line's value is more than, so we know that the true value is bounded above by the secant line and below by the tangent line's value at that x value. Does that make sense?
Yes.
Cool. So that's a good thing to keep in mind. Somebody said something in the chat. There was something covering. How do we find the secant line again? Okay, so to find a secant line is just a line that goes through 2 points, right? So if you know the function and they tell you the two x values, you just find your 2 points, find the slope between them, and use point slope form. So, you know, if I said f of x equals x squared, and I said x equals 1 and x equals 3, you'd say, well, one of those points is the point 1, 1. The other point is the point 3, 9. Find the slope. 9 minus 1 over 3 minus 1 gives me 8 over 2, gives me 4. And then that equation is y minus 1 equals 4 times x minus 1. Or y minus 9 equals 4 times x minus 3. You'll find that if you simplify both of those into slope-intercept, they're exactly the same. Does that make sense? I don't know who asked me that now. Does that make sense, whoever asked that?
Yeah.
Perfect. All right. Okay, secant line, tangent line. And we all know how to find a tangent line. We've done that a million times, right? Find your derivative, that gives you the slope. Know the point, put it into point slope. All good? With finding a tangent line? I hope.
Yes. Yeah.
All right. Cool. In that case, on to area under a curve and integrals and as much of that as we can get to in the next 15 minutes here. So suppose I have a function. There's my function, and I want to approximate the area under the curve. And they will ask you to use a Riemann sum to approximate the area under the curve. You can use a left Riemann sum, which means take a bunch of points along your x values and take the left endpoint of each of those subintervals, make a rectangle going straight horizontally across at each of those values. Okay? They might ask you to do a right rectangular approximation. So we got some function like this. You will take the right endpoints and make your rectangles. Everybody good with the basic of that?
Yep.
So the first two. They might ask you, so this is a left, this is a right. They might ask you to do it using midpoints. So they'd give you some function and they'd mark off some intervals for you. And then they'd say, all right, we need to use the midpoint. So I'd use this value, make a rectangle. I'd use this value and make a rectangle. I'd use this value and make a rectangle. And obviously, the midpoint rectangular approximation method is more accurate than the left or the right. We will note that if we have an increasing function, a left approximation, so we'll just start here. A left approximation, left is less than the true value. If f increases, it is greater than the true value if f is decreasing. And then the opposite of that is true if we have a right rectangular approximation. A right will be, the right rectangular approximation is greater or an increasing, say greater than the true value for an increasing function, and it is less than true value if it's decreasing. Everybody good with that?
Yep.
You should not need to tell if a midpoint rectangular approximation is greater than or equal to. Just know that it's better than the left and it's better than the right. The way you'll do these, if you have equal subintervals, is you'll just, really all you want to do is just find the area of each of the rectangles and sum them together. Pretty straightforward for any of these. The other approximation method that you might end up seeing, and I wouldn't doubt it, is something like this, and we do a trapezoidal approximation. So we go here and we draw a trapezoid. Then we say our next point was here. Say our next point was here. We draw a trapezoid. And our next point was here. We draw a trapezoid. And our next point was here. We draw a trapezoid. And our next point was here. We draw a trapezoid. And we'd sum together the areas of all those trapezoids. That's the trapezoidal rule. If you have equal subintervals, you can just go straight to the formula, but only if you have equal subintervals. The formula is h over 2, where h is equal to b minus a over n. So we'll talk about that in a second. So h, b minus a, b minus a over n over 2 times y naught plus 2y1 plus 2y2 and so on to 2y sub n minus 1 plus a singular y sub n at the end. So you can use that formula if you have equal subintervals. A is the beginning of your interval, B is the end of your interval, N is the number of subintervals. So in this case, it would be 1, 2, 3, 4, 5. So I'd do, whatever B, I'd do B minus A over 5 divided by 2, and then find all these Y values. That's Y naught, that's Y1, that's Y2, Y3, Y4, Y5, until you get to the end. If you don't have equal subintervals, though, you have to individually find the area of each trapezoid. So like if this is from 1 to 2, but this is 2 to 4, we don't have equal subintervals. I have to find the area of the trapezoid that stretches from 1 to 2, then find the area of the trapezoid that stretches from 2 to 4, and so on, and then just sum them all together by hand. Good or no?
Good.
Wonderful. All right, those are your approximation rules. The next thing we need to be able to do before we can even start to integrate is remember how to convert between an integral, a definite integral, and a limit. And so ever since they added this as a topic 3 or 4 years ago, they have put one of these questions on every single year. So if I ask you to convert the integral from 2 to 4 of x squared dx into a limit, you need to know how to do that. It's one relatively easy point on the AP test if you remember how to do it. So we should know that it always is the limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k delta x. Okay? Where delta x is equal to the length of the subinterval. So delta x is always equal to b minus a over n. And where x sub k is how far you go over in each little each little rectangle that you're drawing to get the height of your function. And that will always be equal to 100% of the time, a plus k delta x. Okay, always, 100% of the time. So if you need to convert the integral from 2 to 4 of x squared dx into a limit, your function is x squared. So we'll write limit as n approaches infinity of the sum from k equals 1 to n of x sub k squared. And so x sub k, we'll figure out what that is in a second. That should be 2 plus k times delta x. We got to figure out delta x. Delta x ought to be b minus a, 4 minus 2 over n. So that's just 2 over n. So we have x sub k squared times 2 over n. And we would rewrite that as the limit as n approaches infinity of the sum from k equals 1 to n of 2 plus 2k over n. That's our x sub k squared times 2 over n. And most of the ones I see, they leave it just like this. They don't distribute anything else out. If you have to distribute it out, just be careful with your algebra. I know that earlier this year, I made you guys evaluate these. You will not need to evaluate this summation on the AP test. Sound good?
Yay. Yeah.
That makes life better for everybody, I bet.
Indeed.
Cool. Any questions on that? You need to know these two formulas.
And so because you said we don't need to evaluate, does that mean we don't need to do like the k equals n times n plus 1 thing? Like that's just completely out?
That is correct. I mean, you know, just in case you ever want to, k, sum from k equals 1 to n, also k equals 1 to, k equals 1 to n of k is just n times n plus 1 over 2. This is not technically in the curriculum, so it shouldn't be on there, but if it happened to be, these would be the only two that you might need to know. So I'll write them down here. But the chances of you needing to do that are, I would say, pretty much 0. So those are the ones that you would need to use if you were, for some reason, asked to do that on the AP test. Everybody good with that?
Yeah.
All right. Anybody have any other questions? We're nearing the end of our 2 hours here. So I feel like this is actually a pretty good spot for us to stop. Since we haven't really got into all the integration stuff. So next time I think we'll just pick up with integration. Does anybody have any questions on anything we've done today before I cut the recording and say we're done for today? Yes, we will go over fundamental theorem of calculus next time when we start doing the integral stuff more. And then K is just a way for us to denote the different subintervals. So K equals 1 means the first subinterval, K equals 2 means the second subinterval, and so on. Does that make sense, Karina? Yeah. And then, yeah, Ali answers your question. Any other questions?
Wait, so tomorrow the review session's from like 11 to 1. So are we just doing it the whole time, or is it more of like a drop in and ask sort of thing?
It's not tomorrow.
Oh, not tomorrow, like the next review session, I meant.
Yes. Okay, yeah, the next one, which is Saturday, is that right? Saturday? Yes, yep. Saturday from 11 to 1. I will start off, I will be reviewing the rest of all the integral stuff that we didn't get to today. And then depending on if I can get these practice tests that I haven't been able to get up properly, if I can get those up, we're gonna work through those. If not, I will probably just put some specific problems from those up that I think are really important, and we'll work through them together. And then the last one will be similar to the second one, plus I'll tie up any loose ends people have, talk about all the tips on those sheets that I put up online, and go over any extra FRQs that we have time for. Does that answer your question?
Yeah, thank you.
No problem. Anybody else? Any other questions?
Can it be unrelated to what we talked about today, but related to the test?
Sure.
Okay, so on the like list of calc things to know, I noticed there were things like the integral of like tangent and those kind of things. I don't remember that from class. Maybe I'm just really stupid, but are those things we should know for the test?
It's helpful to know it, whether you know the integral of tangent or not. You should know how to find it. Or if I ask you for the integral of tangent x, you need to do this as a u sub. So you'll write the integral of sine x over cosine x dx. And you'll let u equal cosine x, and du would be negative sine x dx. So you put in your negative and you get negative integral of du over u, and you get negative natural log absolute value u, or negative natural log absolute value cosine x plus your constant. So you don't need to know them. You just need to know how to find them if you don't memorize them. So it's okay if you memorize it to go straight from here to there. Same with for cotangent, it's just natural log absolute value of sine. You can go straight from that to there. But if you don't, just know that you got to split it into sine and cosine and do your u sub.
Got it. Thank you.
No problem. Anybody else? Any other questions?
So you don't have to show work on the multiple choice, or do you?
You do not need to show any work on the multiple choice. Write whatever you need to on the booklet to help you, but you don't need, they will not look at anything from the multiple choice. You need to show all your work and be very clear with your explanations on the free response, because that's where they're looking at all your work.
All right, thanks.
Anybody else? Other questions? All right.